Hi everyone, welcome to the first session on the second iteration of Summa protocol. We don't call it version 2 because we want to emphasize the fact that it's a different way of implementing the protocol. We're coming off from our retreat period. We hope it was relaxing and fun. And we hope that the KZG session that we had with Adria and the some of the other materials are useful, especially for today's talk. They will be very essential for Summa version 2. So we are excited to kick off the second part of the fellowship. And Alex, I'll hand the mic to you.
Thank you. Hi, everyone. My name is Alex Kuzmin, and I'm a ZK circuit engineer in the privacy and scaling exploration team of Ethereum Foundation. As Ali said, we don't really call this version of Summa version 2, but for brevity, I will be calling it version 2 throughout the presentation because the full name of this approach is a polynomial interpolation approach, which is a little bit lengthy. So just for brevity, let's call it version 2. So why, in the first place, why have we started researching anything other than the original version of Summa? Summa v1 is relying on a Merkle sum tree as its main data structure, the main commitment structure. And Merkle sum tree had certain issues with performance. Specifically, when we're generating an inclusion proof for the user, we need to put the Merkle proof inside the ZK snark. And as you can imagine, verifying the hashing operations inside the ZK snark is costly in terms of performance. So we started to look for something that performs better and avoids hashing and overall helps us to simplify the commitment scheme. And the proving and the verifying time, maybe. So we will need some preliminary knowledge from maths to better understand this new approach to Summa. So I assume that many of you are already familiar with such basics as like modular arithmetic, but just in case, let's just quickly verify what it is. So modular arithmetic is not a very difficult concept. We're encountering it every day when we're looking at the clock. Like, for example, 1900 in a 24-hour notation is the same as 7 p.m. And everyone understands that. But if we define that formally, then 19 is equal to 7 modulo 12. So we are actually performing modular division here, and 7 is the remainder of 19 divided by 12. The next convenient thing that we will need from modular arithmetic is the root of unity. The root of unity is a number that modulo p gives us 1. So which means that, I mean, if we, when we exponentiate that root of unity to its order n, we get 1 modulo p. And special case of a root of unity is a primitive root of unity, where no other power of the root of unity yields us 1. So for any k that is smaller than n, we don't get 1 modulo p. And let's take a look at some very specific examples. If we take a very small prime field of size 7 that consists of integers from 0 to 6, we can easily see that we have a couple of roots of unity here, specifically 2 and 4, and both of them are roots of unity modulo 3. So when we do 2 cubed, we get 8, but reduced by modulo 7, it yields us 1. And same goes for 4 cubed, that gives us 64, which is 1 modulo 7. 1 itself is also considered to be a root of unity, but it's a trivial root of unity because, of course, it's obvious that 1 is equal to 1. And then we need to study a certain property of the roots of unity that will be very useful for us in the polynomial interpolation approach of Summa. So the claim is that the sum of all the roots of unity in a finite field is equal to 0. So if we take all those values that, for example, in this previous example, if we sum all the roots of unity, then we are supposed to get 0 modulo the order of the finite field. Let's see how we can try to prove this claim. So here is the statement that we're trying to prove. Let's designate the sum of all roots of unity as capital S. And what we can do next is let's multiply the both sides of the equation by omega minus 1. We can perform such a multiplication because we're sure that omega minus 1 is non-zero. So the multiplication doesn't change the equation. And the next thing that we want to do here is to expand the right-hand side. And we can expand it one by one. First, we multiply omega, and then we multiply minus 1, and write it in this form. Here, we can notice that starting from the second, like in the right half, in the parentheses, starting from the second element, like from omega and on, there is like a repeating part, and we can cancel out those elements. And after canceling out, we can see that the only elements that we're left with are omega to the nth minus 1. So all the right-hand side got simplified to the omega to the nth minus 1, which is exactly the, like if we represent it in a different way, we can think of it as the equation of a root of unity that defines the root of unity. We know that omega to the nth is actually equal to 1. So from that follows that entire right-hand side is equal to 0, because we're subtracting 1 from 1. So now we have this product where we're multiplying two factors, omega minus 1 and s. Obviously, omega minus 1 cannot be 0 here because omega is some root of unity that is some value that is non-zero, non-1, but some other value. But if we have a product that is equal to 0, it means that one of the factors definitely should be equal to 0, and the only factor here that can be equal to 0 is s. So therefore, we have proven that the sum of all roots of unity in the finite field is equal to 0. And to make sure that this is true, we can get back to our very simple example of a finite field modulo 7 and take a look that if we sum up all of our roots of unity, we indeed yield 0. And this concludes the prerequisite mathematical part. So maybe it's time for questions if there are any.
I don't see any questions, Alex, so you can keep going.
Okay, great. Yeah, that was pretty simple. And let's get back to what we were pursuing with Summa v2. So since we said that Merkle tree was a little bit problematic, then we started to look for a data structure that is probably even simpler than a Merkle sum tree. And of course, we want to preserve the privacy. This is out of the question. The privacy should stay on the same level as the V1 solution. And of course, we would like maybe to try to improve the efficiency of the data structure of the commitment phase. So the solution that we employed in version 2 is polynomial interpolation. Let's think for a moment about our commitment structure. The tree-like structure is pretty complex because it has multiple levels and it has a certain way of constructing subsequent levels from the data on the leaf level, where on the leaf level, the original data, if we think about it, is just a list of values. It's the balances of all the exchange users. And if we try to think about some kind of data structure that can be like the most simple data structure that represents a list of values, then mathematically speaking, it is a polynomial because list is something that we understand maybe as software engineers. There is such a data structure, but when we need to do zero-knowledge proofs with this kind of data, there is no such thing as list. So the simplest form of that is a polynomial that goes through all the values that are contained in the list. We can maybe even think about it as some kind of polynomial that we can plot as a graph. And this one is a little bit ugly. And actually, this definitely cannot be a polynomial from Summa because we cannot have negative balances here. But just to have an idea of how can a polynomial represent some set of values or list of values, I decided to include this graph here. So here you can see that this polynomial, of course, goes through a lot of other values, but the values of our interest in question are marked with like fatter red dots, and the polynomial interpolates them. So if we try to define it more formally, more mathematically, so we have a polynomial v capital of x capital that evaluates to each user's balance at a specific point that we designate for each user. For now, we can just think about it as some point x ith. So for if you are the ith user, your index is I, then at the point of xith, the polynomial should evaluate to the value of your user balance. And here we're not interested what happens in between of those user balance points in that polynomial. So the question is, how can we construct on purpose such a polynomial that goes through all the necessary points that we need? And the answer is there is a long-known technique that is called Lagrange interpolation. As you can guess, it was invented by Lagrange a long time ago. And to construct a polynomial that goes through a predefined set of points, first we need to define Lagrange basis polynomials. They have an interesting property that they evaluate to 1 when x capital is equal to x ith here, but for any other x of the set of the given set of possible x values, they evaluate to 0. And here, if we take a look, I'm not sure if you can see my mouse pointer on the screen. Can you?
Yeah, we
Or
can see
not?
it.
Oh, that's great.
Yeah,
So
it's
if
small, but we
we
can see it.
imagine, if we imagine that instead of x capital, we're putting here the x ith, we can see indeed that the numerator and the denominator are just the same, and we're just yielding 1 here. But if we imagine that, for example, we are trying to evaluate this basis polynomial at x third, and at some point when the j going from 1 to n, j is equal to 3, then we will get 0 in the numerator here, and this 0 will effectively render the whole product to be equal to 0. So we can use these basis polynomials to construct the big resulting polynomial by multiplying the corresponding basis polynomial by the evaluation of the desired evaluation of the polynomial at this point. So we from this we can already see that for every corresponding x ith, the evaluation of the polynomial will be b ith, exactly what we're looking for. So if we write that resulting polynomial in more like expanded form, in the coefficient form, we can imagine that it looks somewhat like this, like what we saw maybe even starting from the middle school, like a bunch of coefficients multiplied with the corresponding powers of x. But earlier I mentioned that we want our evaluations, our balances to be at the specific designated user points. And for our purposes, we will choose roots of unity of the finite field as those designated user points. We will later see why it is very useful, and actually this is a common practice in most of the zero-knowledge proof frameworks, but I think you already can guess that since we were talking about the sum of all the roots of unity being equal to 0, the special property that we talked about earlier, then probably this is not a coincidence that we also want the polynomial to have the evaluations exactly at the roots of unity, but not at some other arbitrary points of x. I think here we can make a brief stop for any questions.
Alex, could you go back to slide 22, just one before?
Yeah, sure.
So for a known set of evaluation, should it have been the other way around, xi, bi? Or this is a point, right?
Yeah.
xi,
No, sorry, this is just yeah. Of course, b here is an evaluation, and the x is a point on the x-axis. Sorry, it's just a typo.
and the xi is basically start, 1, 2, 3, and so on.
Yeah. So I here is just like a notion, just index of a user. Yeah.
Yeah, thanks. Anyone else has any other questions before we continue? So the main idea is slowly becoming clear, like user balances will be equal to the ith root of unity, and then we will somehow take advantage of the fact that the sum of all of them will equal to zero. That's
Yeah, but let me
where the
please
advantage will
correct
come
you
from.
that here the balances are the evaluations of the polynomial, like in this equation, the second equation, the lower equation. The balances are the evaluation of the polynomial. So if we have such a polynomial and we know that, for example, we want to check the balance of the 10th user, then what we need to do is we raise omega to the power of 10, and this gives us the x value for that specific user, and we simply evaluate the polynomial at this x value. If we go back to the graph, I think sometimes it's convenient to think in terms of this kind of graph. Like for the user who would fall on the value of 2, the evaluation is like 6 point something here, right? So in the similar way, we are calculating the x value here by raising omega, a root of unity, to a power that corresponds to the index of the user. And we know the evaluation of the polynomial at this point. So let's continue. We have this polynomial, but we are dealing with the proof of solvency, and we're specifically interested in two things. First of all, how do we calculate the total liabilities of the exchange? And second is, how do we prove for the users that they are included in the total liabilities? I think we have a question in the chat. How are users
Yeah,
mapped to indexes? This is not, how to say, this is not essential, at least right now, and maybe we will talk about it later, but basically this is not very important right now. It's just, let's say the most important thing is that the user should know their index, and Exchange can simply communicate this in the form of, I don't know, some kind of user ID. Probably even today, when you log in into the Exchange, you can see your user ID somewhere in your profile page. So yeah, this value is definitely known to you as a user. Is a user equals to the root of unity in the polynomial? Kind of. Not equal to the root of unity, but we're just raising the root of unity to a power of your index as a user, let's say. So yeah, we need one thing that we need here is the proof of your inclusion into such a polynomial. And the second thing that we need is, of course, the total sum of all the liabilities. So for the evaluations of the polynomial here, we also want to have a grand total of all of them. So the question is, how can we effectively calculate this kind of sum? Let's try by simply substituting things in this sum by our expanded values. Like we know the polynomial that evaluates to your specific balance at the ith point, and we can write it down in the coefficient form. And then for the sum of all the users' values, we can write it down and take a look at what it looks like here. So for the user 0, we start with omega to the power of 0, which actually effectively yields 1, but it doesn't matter now. We just want to see the indices because this will be very obvious later what we can do with this kind of representation. So we repeat the same in the second row for the user number 1, then for the user number 2, and so on until we get to the final user. And here we can observe a certain pattern, and we can just start factoring out A's with the corresponding index, with the same index. And here I marked it with different colors. Unfortunately, when I was making the slides, I was trying to fit all the useful information in one slide, not to like lose that the line of thought. But unfortunately, here it's a little bit challenging. But at least I wrote down one of those factorings here, and we can see for any of the colored columns here that we can factor out every of these A's. Like if we factor out A0, we simply get n times A0. When we factor out A1, we get all the powers of omega in the parentheses here. But as we saw in the beginning, in the preliminaries, this sum in the parentheses actually is equal to 0. So here we can see that for all the A's that are not the constant coefficient of the polynomial, but for all the A's with variables, the sum in the parentheses will be equal to 0, which is great news for us because this greatly simplifies our calculation of the grand total of our polynomial evaluations. And the calculation is simply equal to the number of users times the constant coefficient. Once again, to remind you, this comes out from here, from the red column here that doesn't get eliminated, reduced to anything, because there is no sum of the roots of unity as in the subsequent columns. So this means that for our purposes, it is simply enough to construct the polynomial in such a way that the balances of users are placed at the roots of unity. And this automatically gives us, I mean, of course, I'm speaking colloquially here when I'm saying that the balances of users are placed at the roots of unity. But of course, I mean that at a specific root of unity that corresponds to a specific user, the polynomial evaluates to the balance of that user. And since we're constructing the polynomial in such a way, we automatically encode the grand total of all the user balances into the constant coefficient of the polynomial. So this is such an interesting property of a polynomial constructed in such a way, and we will take advantage of that. So now is also a good time to take a pause and answer some questions if there are any.
So just to make sure that everyone understands, liabilities here is like the total, the sum of all balances.
Yeah, the liabilities
Yeah.
of custodian of an exchange is the sum of all the user balances, because this is how much the exchange owes to all the users if the users want to withdraw all their funds. So how do we calculate the total liability? A question from the chat. So this is exactly what we have been doing here, and we were looking for a for a shortcut, for a hacky convenient way to calculate it, and we actually started from the very straightforward, very proper way of calculating this here by just summing up all the evaluations of the polynomial. So we are effectively doing what you would manually do if you had like a list of balances. But then we found out that if the polynomial is constructed in a special way, where we put the balance evaluations at the roots of unity for each user, then we actually get a very nice formula here where the sum of total liabilities is actually just number of users times the constant coefficient of the polynomial. So why is omega like squared, and in other powers the sum of that is also equal to 0? This is a good question. I think here what you can observe is that you can exchange the powers. So you can, for example, you can say that it's an omega squared to the power of n minus 1 here, and do the same everywhere, right? So you're just basically, let's say you're first raising the root of unity to this power outside of the parenthesis, and then you are raising it to the power inside the parenthesis. And if you do that, actually if you raise a root of unity to a power in the finite field, you still get a root of unity. This is still a root of unity. Unfortunately, I cannot like provide you a quick proof for that right now. You can just believe me, but we can see it on a very simple example that we have observed here for our tiny finite field of size 7, that actually 4 is a power of 2. So the roots of unity, like in the finite field, can be powers of each other, and this means that we can exchange the powers here in the parentheses, outside and inside the parentheses, and omega squared will be just a different root of unity, and we will still have a sum of different powers of that root of unity from 0 to n minus 1. So the polynomial B is an interpolation of polynomial B is an interpolation of the balances of all the users. So for every user whose index is I at the point of omega to the power of I, the polynomial value is equal to the balance of that user. So the polynomial is interpolating all the user balances. Okay, if there are no more questions, we can move forward. So now we have achieved the first of our requirements of the Summa protocol, is that if we choose this kind of commitment scheme that is simply a polynomial interpolation, we now know how we can calculate the total liabilities. So the second part that is left is the user inclusion. And here we need to talk about the commitment scheme that we're choosing for our data structure. So our data structure is the polynomial, and we need to commit to the polynomial. And one of the most widely used commitments to a polynomial is the KZG commitment scheme. And
Sorry, Alex.
if I'm okay.
Sorry, before we continue, A0, could you Just go back one. Yeah, the A0, this is coming from the interpolation, right? It's the constant in the big interpolated polynomial, right?
Yeah, so here if we write the polynomial, the big interpolated polynomial in this form, it's the same form that we have been using since, let's say, since middle school. If like I assume that all of us were at least solving quadratic equations in the middle school, looking something like x squared
Yeah.
plus 2x minus 1 equals 0, and in this case minus 1 is exactly the constant coefficient that doesn't have any variable next to it.
Right. And does that
So
constant
yeah,
change when new users come in, for example, and
yeah,
we interpolate again, that changes?
of course, it should change naturally. There is like the intuition behind it may be a little bit hard, but let's once again try to look at something like this graph. Imagine that you're forcing this polynomial. Imagine that you're adding a point somewhere here, like in this place, and you're forcing your interpolated polynomial to go through that point instead of going like whatever it wants right now. So you can imagine that if you're forcing it to go through this point here, then it will probably cross the y-axis somewhere here instead of there. And this is exactly the value of the constant coefficient here when the x is equal to 0. We're getting the evaluation of the constant coefficient. So even if we add a single point here, then we can see that the polynomial will go through the different set of points, and the value
Yeah.
of the constant coefficient will change.
Yeah, perfect. That makes a lot of sense. Thanks.
Yeah, so let's briefly remember what is the KZG commitment scheme. As far as I know, you had a session on KZG just a few days ago. Is that correct?
Yes, that is correct. So you could
Oh yeah,
assume that
this is
everyone should
great.
be familiar by now.
This is great because today we only need to know how KZG works, and we are not really interested in why it works. So how it works, we know that the KZG represents polynomial as a single elliptic curve point. I apologize here for the typo. It's not a finite field element. It's an elliptic curve point. And of course, it preserves privacy of all the users. So when you have that single elliptic curve point, you cannot make out the individual user balances from a single point. And of course, there is an opening, there is a way to reveal the values that went into the commitment, or colloquially speaking, open the commitment. So yeah, this, as I said, the commitment is that elliptic curve point. It uniquely represents our polynomial, and the prover can generate a succinct opening proof that verifies that at a given value of x, the polynomial evaluates to a certain evaluation without revealing the rest of the polynomial. So to recap who knows what and who does what, the prover knows the entire polynomial. The prover knows everything in our setup, and the prover can generate the commitment, that's elliptic curve point. And also the prover for any value of x can generate a proof that the polynomial evaluates to a certain value at that value of x. Verifier here is interested in checking the proof at a specific value of x. Like, for example, in our particular case, you as an exchange user you know your index I, and you're expecting the prover to provide you the proof for this specific point on the x-axis, so you know that point. Oh, sorry, there's also a typo. Of course, the verifier doesn't know B. It's impossible. So, oh, no, it's not a typo. There is like, how to say, mistake with variable naming. Here should be the x capital. So the prover knows the polynomial, not just the evaluation of the polynomial, but the entire polynomial b of x. But you, as a user of Exchange, you only know your balance. So you know the evaluation of the polynomial, which is b of omega to the power of I. So you know your index and your point on the x-axis, and you know your balance, which is the evaluation of the polynomial at this specific point. And if the prover gives you the proof, then you can, by using the proof and the elliptic curve point that is a KZG commitment, you can conclude that the verifier is not lying to you when opening the evaluation of the polynomial at your specific point. And at the same time, you are not learning anything else about like any other users. So privacy is preserved. And to recap, what we have learned today is that in this next iteration of Summa, we are using a polynomial as the data structure, and it's probably the simplest data structure that we can imagine for a simple list of balances, list of values. So the grand total sum of the liabilities is automatically, or we can say automagically encoded in the constant coefficient of the polynomial, thanks to the specific way of how we interpolate the balances, thanks to us putting the balances exactly at the roots of unity. So the prover commits to the polynomial. So in our case, the exchange or the custodian will commit to this kind of polynomial using a KZG commitment scheme and make this commitment public, the commitment value public for anyone to verify. And then the prover also needs to provide at least two openings here. The first of the openings is the opening of the polynomial at x equals 0, which effectively gives us the constant coefficient of the polynomial. And this is actually an opening that we need to calculate the grand total, the total liabilities of the exchange. We simply multiplied the constant coefficient by the number of users that the prover should reveal. And the second opening that the prover needs to provide is the user inclusion opening proof. And this is provided individually, of course, in private, so the prover can communicate that value to every user of the exchange individually. And I think this concludes my talk today. Yeah, this thank you should be the next slide, but it just stuck together. So if you have any
Thank you, Alex.
questions,
This was great. Yeah, this was great. So because the opening now, the points are not random, right? As usual, when we are checking that the approver
yes.
knows the entire polynomial, the security here relies on at least a big number of users actually verifying the proof, right? So the more the better, basically. The more users actually verify their proof, the better for the
Um,
security. Unlike the usual case where a few random openings will make us believe that the prover knows the polynomial, right?
Here I'm not sure if maybe if we try to take a look from the other perspective, like what attack vector are you talking about when you're talking about security? Are you implying that the prover can try to construct like an invalid polynomial that doesn't include all of the users, for example, or
Yeah,
includes
let's
zero
say,
balances for some users, right?
let's say the prover interpolated correctly in all the points except one, for example.
Mm-hmm.
Um,
Yeah,
now,
this is
let's say,
unfortunately, this kind of attack vector, it stays the same as with the Merkle sum tree. Like, of course, if we could, of course, we would try to do better than Merkle sum tree in this extent, but this vector of attack stays the same. Uh, in a similar way as in the Merkle sum tree, you simply, if you just don't include a user into the tree, no one will know about that. Like there is no way to do anything about that. So here, if you don't include a user into the polynomial, then of course grand total will be adjusted accordingly. Like the grand total will be less than the real value. And unfortunately, yeah, this is the culprit of all kinds of proofs of solvency today.
so we have two questions, Alex, on the chats.
I see. So the first question is, does representing polynomial, does choosing a data structure as a polynomial lead to any kind of storage inefficiencies? And how big is the polynomial? Well, the polynomial is as big as the number of users. For example, if your exchange has 1,000,000 users, then you need a polynomial that interpolates 1,000,000 values. And so we're talking about if, of course, if the value is 1 byte, it would be a megabyte, but of course the value is not 1 byte, so it will be several megabytes per million. And if we have several million users, of course, it's just like tens of megabytes, which is still acceptable, I would say. So this is not much of an issue. And how do we deal with floating point numbers? Well, here nothing has changed since Summa v1. So we are just using like big integers to represent the decimals of balances. So the big integers are big enough. If we multiply our fractional value of balance by a large enough number, then we're not losing any precision. So this hasn't changed since Summa v1. And there is, I think, yeah, fixed point math. And Enrico has answered the first question that actually, yeah, this is, but here, yeah, I can expand even more on this topic. So we're dealing with two things when we're doing proof of solvency. We're dealing with the commitment phase and with the opening phase. And for the commitment phase, we have to construct the entire data structure that we're choosing. And here Enrico is right that while we're building the data structure here, we are already more efficient than the Merkle tree because we eventually need to construct the entire Merkle tree to prove an inclusion of even a single user. So which means that at least once per the round of solvency, we're constructing the entire Merkle tree. And as Enrico said, of course, when we're constructing a tree, we occupy much more space in memory than when we are simply listing, let's say, listing the balance values. Of course, it's oversimplified how we interpolate the polynomial, but essentially it's similar to just writing down the list of balance values. because we don't have any kinds of intermediate node hashes that go from the leaf level to the root. We don't have that tree structure here. So it's like the leaf. So, I mean, if we go even further and we compare directly the Merkle tree and the polynomial, then a polynomial is simply the leaf level of your Merkle tree, let's say, again, oversimplified. So roughly the polynomial occupies as much space as the leaf level of your Merkle tree, but the tree also has all the subsequent levels and up to the root. So for 300 million users, the degree of the polynomial should be higher than 300 million, which is the next power of 2. We are constrained to working with powers of 2 because of the underlying ZK math. So we can just fill the rest with zeros.
I'm wondering, Alex,
But
if you guys are thinking about recursion, and if there's a way to um, recursively aggregate all the proofs of all the users into a single grand proof, while at the same time preserving privacy somehow. So the user balances are not public input or anything. Are you guys thinking about that at all, or is that in principle something possible?
Well, I think I'm just trying to read between the lines a little bit. And let's first talk about what is public, what is private, and remember that the verifier doesn't get to know any other balances and any other data about the polynomial. The verifier only knows their own balance and also the opening proof of the constant coefficient that yields the grand total. And regarding the recursion, let me ask you a question just to clarify. Are you trying to like find a way to maybe break down the proof into smaller pieces just to optimize it?
No, we have all the proofs for all the users. Let's say
Mm-hmm.
the prover already now, the custodian of a sex, already
Mm-hmm.
generates those proofs, right?
Yeah.
If you have um, uh, 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 a circuit that accepts the verifiers of the verifier of each of these proofs, which is the same verifier, right? But it would prove that, yeah, I have seen this number of proofs for all the users. So it would be, you would zip all the proofs for all the users into one aggregated proof.
Um,
I don't know if in
we
principle
I,
that is
I'm
something
afraid
possible.
that this is not uh, how to say this is not feasible for the same reason as if in V1 you could imagine that we can create a ZK proof of a Merkle path without revealing the balances that went into the leaf. Like, for example, we are giving you the hash. We're giving you the hash of the leaf and the subsequent Merkle path elements. This is great for you because you can actually make sure that this hash value is correct. You simply hash your exchange ID and your balances, and you can verify that. But if I give you some other user's ZK proof, you will not be able to verify it because you simply don't know the real balance of that user. And this is the main issue with any kind of like batch proving, aggregation, or making the proofs absolutely non-revealing and providing them to the wider public, because no one else can verify your balance. This is the argument of knowledge. This is not the argument. This is knowledge soundness here. It's like only you know the value, and only you can verify that value. Of course, you and the exchange in our case.
But the prover, though, the prover has the balances of all the users, and they are generating one proof per user.
Yeah, sure,
So,
but but if I give you a proof that includes other proofs inside it, of course, I should give it to you in such a way that this proof doesn't reveal the actual values of the balances. For example, I can give you such a proof. Let's imagine that, not in this case, but hypothetically, I give you a proof where you can verify your own balance, and also you can see that other 10 proofs for other users are passing. The verification is passing. But of course, I, as an exchange, I will not let you see their balances. And in this case, you will see that you can verify some proofs here, but you just cannot be sure that they are real, that they actually prove anything about like real data. Yeah, and even as Enrico says, even if you see their balances, it's meaningless, because probably you will have to like find those people, give them a call, and ask them, all of them, like, hey, is your balance this? Is your balance that? And of course, you will not be doing that.
yeah, that makes sense. Yeah, I still relies on the fact that each users verify that this proof made actual sense. Yeah,
Yes.
yeah, makes sense. Excellent. Any other questions from anyone before we wrap up? Alex, could you give just a quick teaser about Wednesday? Wednesday we have another session, right? So that will be about what exactly?
Yeah, on Wednesday, we will take a look how we can actually use Halo 2 to achieve all of the above, because as you can see, we're doing some things here that are like computationally intensive, like KSG commitment. And of course, we don't want to prove anything like that inside the circuit. So we will see a very interesting and hacky way how we can use Halo 2 to achieve KSG commitment for free and quickly generate the opening proofs, including maybe some optimizations to the opening proofs generation. We will also briefly touch on how we can split the polynomial into as many pieces as we need without losing any of the desired properties. And also, I'm a little bit surprised. No one has asked a question, how can a user make sure that maybe if the user has the same balance as another user, that the commitment they receive is not shared between multiple users who have the same balance, and the exchange is just including only one of those balances into the interpolated polynomial without like letting users know. And this way, the exchange is just understating the reliabilities. So I think we can start the Wednesday session from a little trick that we can use to mitigate that.
Yeah, that is a very interesting point. So looking forward to that. There is one last question, I believe, in the chat.
Mhm. A quick search yields nothing but multivariate KZG and some check. This I don't could you please elaborate on this question if you can? to reduce degree, multivariate KZG and some checks. So, well, I can try to guess the question here, which still I don't see here, but I assume that question is, can we use the multivariate KZG and a sum check protocol to reduce, like to improve something? And the answer is yes, probably we can. And this will be the next iteration of Summa, actually. But just like how to say, thinking about the said storage inefficiencies, if we can say, if you have like 300 million users, you have to commit to 300 million user balances. And your data structure, at least the initial data structure before the commitment, should include all 300 million user balances. You cannot just exclude some of the users from your data structure. If you do that, you're just understating your liabilities. So you can find a super optimized data structure, but it will still include all of your users. I mean, it has to, like, there is no other way. We can talk about other performance improvements, maybe, such as the prover time or verifier time. And this is a good topic, and we will get to that because we already have the benchmarks of V2 of this polynomial encoding approach. So we can already compare like what happens when we're using a polynomial instead of a tree, how it affects the performance. And we have some publicly available benchmarks of other existing solutions, such as Binance, who is using a Merkle tree, but in a very different way from us. And we can compare the performance here. Yeah. But not
Excellent.
the storage, amount.
Excellent. So looking forward to that, Alex. Thank you so much for today's session. And I think we can
Thank
wrap up
you.
here and see you guys on Wednesday.
Thank you.